Welcome to the fourth video in this four-video series on logarithmic and exponential functions. In this video, we use logarithm and exponential functions to solve real-life applications. Here's the first example. I'll pause while you read this. Okay, before we get into this problem, I'd like to start by just sharing some general information for you. This is the equation that models exponential growth. And in this equation, you'll see there are 5 letters. Let's go over the significance of each of them. In this exponential growth model, y represents the quantity of interest. In this particular problem, the quantity that we're interested in measuring is the population of the city. So y would represent population in this problem. T represents time, a fitting letter choice for such a variable. E is its usual value of 2.718 approximately. And A and K represent constants that will vary from problem to problem. We'll talk more about that later. Let's see how we can use this exponential growth model to solve this particular problem. First, let me say when a mathematician says model, they mean equation, essentially. But although it's an equation that represents something in real life. So to complete this growth model, I need to find the values of A and K. Remember, E is 2.718. Y and T are the actual variables in this problem. They change over time. But A and K are constants that we don't know yet. And if we can know those constants, then we can ultimately answer the question to predict the model's population in 2030. But to complete an exponential growth model, the first thing I like to do is choose a time zero. The time zero is an interesting concept. Let's look at it this way. In this problem, they mention the year 2002, 2015, and 2030. What are those numbers? What does 2030 mean? 2030 what? Well, doesn't it mean 2030 years since the birth of Christ? Okay, well, it seems like society has chosen the birth of Christ as a choosing of time zero, a resetting of the clock in some sense. But I'm not going to use that time zero. I'm going to use 2002 as my time zero. Now, that is just a little math trick that's going to make the algebra much, much easier in this problem. Now, what does it mean that 2002 is my choice of time zero? Does it mean that this city didn't exist before 2002? I'm quite sure that's not the case. If there were 1.5 million people there in 2002, the city must have been there long before that. 1.5 million people didn't arbitrarily on one day show up in 2002 in a giant empty field and form a city. So while the city may have been there before 2002, I'm going to consider that the beginning of the problem. I chose that because it's the first year in the problem. Now, as we go on, you'll see how the choosing of time zero to be the earliest year mentioned in the problem can be really helpful for algebraic purposes. So now what I'm going to do is set about the business of finding A and then finding K. My goal is this. A and K are certain numbers, and I don't know them yet. And if I can find them, then I'll be able ultimately to make the prediction of this city's population in 2030. But before I get to that prediction, let's get back to finding A and K. So what I do to find A and K is I pick a fact from the problem. You may see it in pink right now. From 1.5 million in the year 2002, meaning that the population was 1.5 million in the year 2002. Well, I'm going to convert that to a mathematical statement that I can use in my equation using the concept of time zero. If I've arbitrarily chosen 2002 as time zero, then I can make the statement that when time is 0, y is 1.5. I'm going to use y as 1.5 instead of 1.5 million, And just remember that y is measured in millions. So now I'm going to take that and plug them into the equation, as you can see I've done here. Now, if you saw video 3, then you know a little bit about solving these kinds of equations. Let's go about the business of solving this. First of all, the expression on the right side, let's analyze that. We don't know what k is yet, right? But we do know what k times 0 is. And we know that any non-zero to the 0 power, e to the 0 in this case, is 1. And since anything times 1 is itself, the entire right side of that equation works out to just a. Okay, well now that I know the value of a, I can plug that into my model. You may see it in light blue here. Notice I've replaced a with 1.5. Now that I've found a, let's go about the business of finishing to complete this model. I have a, but I do not know the value of k yet. So here's a clever trick I could do to find k. Here's another fact mentioned in the problem that I haven't used yet. You may see it in pink. And it tells us that there were 1.8 million people in 2015. Let me convert that to a mathematical statement that I can use in my model. At time 13, y is 1.8. Why time 13? Well, if time 2002 is my, quote, beginning of time, then the year 2015 was 13 years later. In other words, 13 years after the, quote, beginning of this problem, the population was 1.8 million, or y is 1.8. I can now plug that into my latest version of the model, as you can see I've done here. And again, going back to video 3 of this series, will show us how to solve this equation. So a couple of reminders from video 3. I have this equation with an exponential function. I have to isolate the exponential function, so I'm going to divide both sides by 1.5. I could simplify the fraction on the left, but I'm choosing not to. As you'll see, it won't matter. I'm then converting from exponential to logarithmic form. Remember, ln represents log base e. And now to solve for k, I'm dividing both sides by 13. Now I recommend at this point hitting pause, getting a calculator, and typing that expression in for k and getting a decimal. Hit pause now. You should have gotten something like this decimal for k. Before we continue, I want to talk about something called significant figures. These models are very sensitive to the values of k, and small changes in k can have big impacts on the final answer depending on how you round. So I recommend rounding k to at least 4 significant figures, or even more. Significant figures means starting with the first non-zero number, go that many decimal places. So I would go to at least 4 significant figures for k every time. Well, what have I done here? I've now found k, so I can plug k into my model. And now I've done something called completing the model. Let's review what we've done here. We started with an exponential growth model. We used some information in the problem, our time 0 information, to find the value of a. Then we used additional information in the problem, something that happened after time 0, to set up a logarithmic exponential equation that would lead us to the completion of this model. Now that I have the model, and only now that I know the values of a and k, am I able to make this prediction here. You may see it in pink. We want to predict the population in the year 2030. Well, we can't plug 2030 in for time here because we've reset the clock in such a way that the year 2002, as society knows it now, is time 0 in this problem. Well, if 2002 is time 0, 2030 is 28 years after that. Therefore, I'm going to answer my question by taking my model and plugging in 28 for the value of t. I recommend at this point hitting pause and practicing typing this into your calculator and getting y as a value. Go ahead and hit pause now. Typing that in your calculator should have given you approximately 2.2, and that represents 2.2 million people as our population prediction for the year 2030. And before we go on to our next problem, I want to take another look at what things represent in the exponential growth model. Y represents the quantity of interest, which in this case was population. T represents time. E is always 2.718 approximately. And most notably, A and K are the constants that vary from problem to problem. In the problem we just finished, A was 1.5 and K was some decimal, and those did not change throughout that problem. But of course, when we go on to another problem, something that isn't about this particular city, A and K will of course take on different values. So they're constant throughout a problem, but they're of course not constant from problem to problem. Let's take a look at an example of something called exponential decay in a half-life problem. I'll pause while you read this. Okay, before we start this problem, let's talk about what half-life and decay mean. Decay, strange as a word as it is, in mathematics just means a quantity that's decreasing. And half-life refers to a situation in which half of a particular substance dissipates in a fixed period of time. Here's an example. When we say that the half-life of something is 8 days, consider the following example. I haven't started this problem yet, and none of these numbers are really from the problem, but suppose we had 60 grams of a substance at the beginning. In this case, it's radioactive iodine. And to say that it has a half-life of 8 days means that 8 days later, half of what was there has dissipated. Now, this doesn't mean that the entire 60 grams sits around and then on day 8, half of it just vanishes into thin air. This is something that's slowly decreasing or decaying over time in such a way that every 8 days, half of the original amount remains. So 8 days later than that, on day 16, we would have half of the 30 grams, which would be 15. And then 8 days later, on day 24, we would have half of 15, which is 7.5. Now again, there's no 60 grams mentioned in this problem. This is just an example of how half-life works. Now, on to the actual problem we're doing. Because they say that this is a radioactive decay problem, it turns out that is also modelable by the exponential growth formula. So the same formula that we used for the population of the city just now can be used to model the percentage of a particular radioactive sample that remains on any given day. So let's talk about the variables. Y, in this case, is going to represent the percentage of the original sample that remains on any given day. T is going to be the day number. A and K are going to be constants particular to this problem that we don't know yet. And E, of course, is 2.718 approximately. Okay, so I like to start using my exponential growth or decay formula by choosing a time 0. Now, if you'll notice, the dates in July are July 6th and 26th are given in the problem, but I don't want to use the numbers 6 and 26th. So I'm going to declare a time 0. July 6th will work as well as anything here. I typically like to choose the earliest mention of any data in the problem, which is July 6th, or the creation of this particular iodine sample. And just like we did before, we have to make it our goal, our temporary mission here, to find the values of A and K that are particular to this problem. And this has to be done before we can answer the question in the problem. This is called building or completing the model. So let's go about the business of finding A and K. Well, the way we always find A and K is by plugging in values for the variables, y and t, that we know to be true for the problem. So, for example, since the sample was created on July 6th, we're to assume that it had 100% of its original amount on the day of its creation, by definition. And so we can mathematically convert that into, when t is 0, y would be 100%. I'm going to plug those into my formula, and that's going to allow me to solve for A, because, as we know, k times 0 is 0, e to the 0 is 1, and a times 1 is a, thus giving us the value of A. So in this problem, we'll use A to be 100%. So I can take my model and replace A with 100%. I'm now half done building my model. I have the value of A. I still need the value of K. Well, in order to find K, we're going to need to find another real-life data point from this problem, some point in time that we know the value of Y. See if you can follow this logic. If the half-life of this particular substance is 8 days, and it was created on July 6th, then wouldn't 50% of it remain 8 days later, i.e. on July 14th, which is day 8? Of course it would. Now, this information was not given in the problem, but had to be deduced by the understanding of what half-life is. So now I can convert that into a mathematical statement. Since July 6th is times 0, I can say when t is 8, or on day 8, y is 50%, or 50% of the substance remains. And I can plug that in to the y and t in my formula, as I've done here. Now by doing this, we're going to be able to solve for k. So if you watched video 3 of this series, we'll use those techniques to isolate the exponential function, convert to a logarithmic function, and ultimately solve for k, which is in the exponent or argument of my exponential function. So to isolate the exponential, I thought it would be wise to divide by 100%. 50% divided by 100% reduces to a half. And now I'm in exponential form. I can convert to logarithmic form by applying the natural logarithm to both sides, and then solve for k by dividing both sides by 8. This, when typed into a calculator, gives a value of k. Remember, when approximating k, it's good to go at least 4 significant figures, meaning starting with the first non-zero digit, or 8, go 4 figures out. And now that I have my value of k, I've completed the model because I simply substitute that k that I found into my model, and I now have the model created. Remember, all of this model creation gets done before we ever address the question. Now I'm ready to address the question, what percentage of the original sample will remain on July 26th? Well, that's like saying find y when t is 20. Why is that? Because July 26th would be day 20 if the sample were created on July 6th as my day 0. In other words, 26 minus 6 is 20. And I can plug that in for t, 20 I mean, and when I do that, all I have to do is type this into a calculator. I'm going to recommend that you hit pause, type that in a calculator, and see if you get what I get. Hit pause now. Hopefully, you got about 17.678%, which is approximately 18. And what does this mean? Well, we plugged in 20 for T and got 18% for Y. That means that about 18% of the original iodine will remain on July 26, thus answering the question. Before we go on to our third problem, this might be a good time to stop and reflect on what we've done so far. In the first problem, we looked at a city's population, and we modeled its exponential growth using this formula. Now, while we didn't graph it at the time, you might imagine that a city's population graph, if it were growing exponentially, might look something like this. Then, we looked at an iodine half-life problem as an example of exponential decay or decline, using the same formula, but studying a quantity that was decreasing over time, as the iodine was. Well, how can the same formula model two seemingly different looking behaviors in nature? Well, it turns out that it does. And what makes these different is whether the value of k is positive or negative. Well, I didn't point it out at the time. K was a positive value in our first problem and a negative value in our second problem. As we transition into our next and final problem, we're going to look at something a little different. It's called Newton's law of cooling, and it tracks the temperature of an object over time when that object starts out hotter than room temperature, such as a cup of coffee. And you might imagine over time, if you were tracking the temperature of a cup of coffee, that if there were a certain room temperature, call it R, that the temperature of the coffee would be decreasing over time, but getting closer and closer to that room temperature as time went on. The distinction between this and exponential decay is that in this case, the quantity approaches that R value over time, whereas if you look at the upper right corner, in exponential decay, whatever measured quantity we're studying approaches zero over time. And when we have behavior such as you see at the bottom of your screen, some quantity approaching a value of R instead of zero, then the formula is slightly different. It will be the R value plus the exponential decay formula. And that's the concept that we're going to be looking at as we move to this third and final problem on Newton's law of cooling. So here's the actual example we're going to solve using Newton's law of cooling. Okay, here's the formula that we're going to use to model the temperature of the coffee over time. So in this problem, Y represents temperature, T represents time, A and K are, as usual, constants we don't know yet, and E, of course, is about 2.718. Now, the first thing worth noting here is because the room temperature here is 70 degrees, then I put that as an added term in front of my exponential decay formula to model the temperature of this coffee. So let's go through the same process we did in the previous problems. First, we're going to choose a time zero. Well, it seems logical to me to let time zero be the time of the pouring of the coffee, which was 10:05 a.m. And we're going to now find A and K, just like we always have, by finding particular data points that we can plug in for Y and T that represent the temperature and time of this coffee at known moments. Well, let's start with this one. The fact that the coffee was poured at time zero, or 10:05, and had a 180-degree temperature. Mathematically, that's the same as saying when T is zero, y is 180. So I'm going to take y and t, plug in 0 and 180, and I'm going to solve for whatever I can. In this case, I can solve for a. Notice the e to the k times 0 factor. We don't know what k is, but of course k times 0 is 0, e to the 0 is 1, and a times 1 is a. Subtracting 70 from both sides gives me a quick answer for my value of a in this particular problem. So I'm going to take the a in my model and replace it with 110. I'm now half done building my model. I now have to go about the business of finding the value of k to have a completed model, and only then can I answer the question about the coffee that I'd like to know. So continuing in the process of finding k, as we always have, we need to find some other data point to plug in for y and t. We know, additionally, that by 10:20 a.m., the coffee temperature had reduced to 160 degrees. Well, if time 0 is 10:05, then 10:20 is 15 minutes or a quarter of an hour later. So I could use a t value of either 15 or 1/4, depending on if I wanted to use minutes or hours. To avoid fraction, I'm going to use minutes as my measurement of time. So I'm going to say when t is 15, in other words, 15 minutes after the pouring of the coffee, the temperature was 160. I'm going to plug those values in for y and t here. And this will enable me to solve for k, complete my model, and then ultimately answer the question I want to know. Again, referencing video 3 in this series, that will enable us to solve for k here. And to do that, I need to isolate the exponential function, meaning the e to the 15k. So to isolate that, I'm going to subtract 70 from both sides. I did not show the actual work here, but I did subtract 70 from both sides. And then the next step and final step in isolating the exponential function is dividing by 110. Notice the fraction 90 over 110. I could reduce that to 9 over 11, but it's something I didn't bother to do, and it won't matter since I'm using a calculator anyways. Now notice I've isolated the exponential function. To actually solve for k now, I should convert from exponential form to logarithmic form. Notice the natural log on the left side of the equation. And ultimately, to solve for k now, I should divide by 15, and there's what I get. I recommend hitting pause and typing that in a calculator and seeing what you get. Hit pause now. Hopefully you got this value. Notice I've rounded to 4 significant figures for the value of k, as I often do. Now we have a completed model because all we had to do was substitute the newly found k value back into the model, and now I'm done with that portion of this problem. So completing the model is what we do before we can address the question. Now we're ready to address the question, find the temperature of the coffee at 11:40 a.m. Well, the coffee was poured at 10:05, so 10:40 is 35 minutes later. This question I'm trying to answer is equivalent to find y when t is 35, meaning 35 minutes after the pouring of the coffee. So I'm going to take my value of t, plug in 35, and this should give me the temperature of the coffee at that time. Once again, I'm going to recommend hitting pause here to see if you can calculate this properly. Hit pause now and calculate this value. You should have gotten about 138.87 which to the nearest degree rounds up to 139. Remember, y represents temperature, so ultimately we have just found an approximation for the temperature of this coffee at 10:40 a.m. That completes this problem and this fourth video and this series on logarithmic and exponential functions.